You look up, the sky is blue. Obvious, right? You've seen it your entire life. Blue sky, white clouds, that's just how things are. But here's a question. Why is it blue? Go ahead, think about it. What's your answer? Most people say something vague. That's just the color of air. Or it reflects the ocean. Or my favorite, because of the atmosphere. But those aren't answers. Those are just words. They don't explain anything. What is it about air, about the atmosphere, that makes it blue? And more importantly, why blue specifically? Why not green? Why not red? Why not no color at all? The truth is stranger than you think. The sky isn't blue because of anything inherently blue up there. There's no blue paint, no blue substance, nothing colored floating around. The sky is blue because of something far more fundamental. It's blue because of the size of molecules compared to the wavelength of light. And when you understand why that matters, when you see the actual mechanism, you realize that the color of the sky is telling you something deep about how light and matter interact at the smallest scales. Let me show you what I mean. First, let's clear up what we're actually looking at when we look up. Air, that's it. Nitrogen, oxygen, a bit of argon, some water vapor, carbon dioxide, mostly nitrogen and oxygen, about 78% and 21% respectively. These are invisible gases, completely transparent. If you trap air in a jar and look at it, you see nothing. It's clear. So how can clear, invisible air produce blue light? It can't, not directly. The blue isn't coming from the air. It's coming from the sun. The sun is sending white light toward us, and white light isn't actually white. It's a mixture. Red, orange, yellow, green, blue, violet, all mixed together. When you mix all those colors, you get white. That's what sunlight is, a combination of all visible wavelengths traveling together. Now, that white light hits the atmosphere. It encounters molecules, nitrogen, oxygen, all those invisible particles floating around. And here's where something extraordinary happens. Those molecules scatter the light. They take the incoming light and redirect it in all directions. Some goes forward, some goes sideways, some goes backward. This scattering is why we can see the sky at all. If there were no atmosphere, if you stood on the moon and looked up, you'd see black, total darkness, even during the day, because there's nothing to scatter the sunlight towards your eyes. On Earth, we have air. The air scatters sunlight. That scattered light reaches your eyes from all directions. That's what the sky is, scattered sunlight. But wait, if the sun sends white light and the air scatters it, shouldn't the sky be white? All colors scattered equally should still look white, right? That's the question that breaks everything open. Because the answer is no, and understanding why that's no is understanding why the sky is blue. Here's the key. The scattering is not equal. Different colors scatter differently. And the reason for that is almost absurdly simple. It's because different colors have different wavelengths. Red light has a long wavelength, about 700 nanometers. Blue light has a short wavelength, about 450 nanometers. The molecules in the air are small, very small. A nitrogen molecule is about 0.3 nanometers across. That's tiny. Much, much smaller than the wavelength of visible light. And here's the rule. When light encounters something much smaller than its wavelength, the amount of scattering You've seen them. The sun near the horizon, the sky turns red, orange, pink. Beautiful. But why? If blue scatters more, why does the sky turn red at sunset? Here's what's happening. When the sun is overhead, sunlight travels a short distance through the atmosphere before reaching your eyes. Some blue light gets scattered out, but there's still plenty of all colors left. The sun looks white or slightly yellow. But at sunset, the sun is near the horizon. The light has to travel through much more atmosphere to reach you. Miles and miles of air. As the light passes through all that air, the blue gets scattered away, scattered and scattered and scattered, until almost none of it is left traveling in the original direction. What's left? The red. Red scatters less, so it survives the long journey through the atmosphere. That's why the sun looks red at sunset. This is beautiful. The same mechanism, Rayleigh's scattering, explains both the blue sky and the red sunset. It's all one phenomenon. Blue scatters more, so when you look at scattered light, you see blue. Red scatters less, so when you look at transmitted light that's traveled a long distance, you see red. Two effects, one cause. Here's something else. Clouds. Clouds are white. Why? They're made of water, and water is transparent. So why don't clouds scatter blue light like air does? Because the particles in clouds are too big. A water droplet in a cloud is about 10 micrometers across. That's much larger than the wavelength of visible light. When light encounters particles larger than its wavelength, the scattering is different. It's called my-scattering. And my-scattering doesn't depend much on wavelength. All colors scatter roughly equally. White light in, white light out. Clouds are white because the water droplets are big. This tells you something profound. The color of scattered light depends on the size of the scattering particles. Tiny particles, smaller than the wavelength, you get Rayleigh scattering. Blue sky, big particles, larger than the wavelength, you get my-scattering. White clouds, you can look at the color and deduce the size of the particles. The universe is telling you something just by the color you see. But this isn't just about pretty skies and sunsets. This mechanism shows up everywhere. And when you start seeing it, you realize how fundamental it really is. Let me show you why this matters beyond pretty skies. Rayleigh scattering isn't just an atmospheric phenomenon. It's fundamental. It happens whenever light interacts with particles much smaller than its wavelength, and that happens everywhere. In space, light from distant stars passes through clouds of gas and dust. The blue light scatters more, gets removed from the beam. The star looks redder than it actually is. We call this interstellar reddening. Astronomers have to correct for it when they measure the properties of stars. If they don't account for Rayleigh scattering, they get the wrong answer. In biology, light scattering in tissue is mostly Rayleigh scattering. That's why veins look blue under your skin, even though the blood inside is red. The red light penetrates deeper. The blue scatters back out. In material science, the color of sapphires comes from Rayleigh scattering by tiny impurities. The blue of a sapphire is the same blue as the sky. Same mechanism, different context. And here's the deepest part. Rayleigh scattering is a consequence of how electromagnetic fields interact with matter. When light hits a molecule, it shakes the electrons in that molecule. The electrons oscillate at the same frequency as the incoming light, and oscillating charges radiate electromagnetic waves. That's the scattered light. The reason shorter wavelengths scatter more is because higher frequency light oscillates faster, shakes the electrons harder, and produces stronger emission. The 1 over lambda to the fourth law comes directly from Maxwell's equations. The same equations that describe how radios work, how magnets work, how light propagates, it's all connected. So when you look at the blue sky, you're seeing Maxwell's equations in action. You're seeing the interaction between light and matter at the atomic scale. That blue color is proof of the wave nature of light, of atomic structure, of electromagnetic theory. It's not just pretty, it's physics. And here's what I love about this. You can understand it. You don't need complicated math. You need to know that light is a wave, that molecules are small, and that waves interact with small things differently depending on their wavelength. That's it. From those simple facts, you can derive why the sky is blue, why sunsets are red, why clouds are white. One mechanism, many consequences. This is what physics is supposed to do. Take something familiar, something you see every day, and reveal the mechanism underneath. The sky isn't just blue. It's blue for a reason. And that reason connects to everything else we know about light, matter, and electromagnetism. So next time you look up, remember, that blue isn't paint. It's scattered sunlight. It's photons ricocheting off nitrogen and oxygen molecules. It's wavelength-dependent scattering following a 1 over lambda to the fourth law. It's Maxwell's equations playing out across the entire sky. And the fact that we figured this out, that we can explain it, calculate it, predict it, that's one of the greatest triumphs of physics. We looked at something beautiful and asked why, and we found the answer. That's the joy of understanding, not comfort, not mystery, truth.